Hello everyone, in this video I will show you this very interesting project that I have here on the bench. This is a power stabilizer. It's the solution on how to get a steady and clean 13.8 volts from any source of 8 volts up to 40 volts DC. So here, for example, you can see I have it right on with one battery for a Milwaukee tool. It's a 12-volt battery. It's not even fully charged. It's around 11 volts. And we are having on the output, as you can see here on the display, constant and a solid 13.75 volts all the times. So in this video, we will cover motivations, the cost of the parts, the constructions, and the test of this device, which is going to be very useful for your radio station or for portable operations like POTA or similar, since you can throw any kind of batteries from any voltage to this device, so you can operate mostly continuous on the field. And in case, of course, of emergency, any batteries that you have around will help you to continue to operate your station with a solution like this. So we already covered in the first part why I am building this project. Here there is a quick summary: clean and stable 13.8 volts, using any kind of batteries, using any kind of available power supplies, especially the unsuitable ones. And what that I means with this, you can connect, for example, a 12-volt power supply from a PC or a server. Those are power supplies. They really come very high amperage. So you will see I have one that I tested later on the video, and then this will take the 12 volts from computer power supply, and it will convert it to automatically 13.8 volts. And with this, you avoid to have to touch or manipulate the computer power supply or the server power supply in any way. So also we want to make it small to carry for portable operations. I mentioned that. And also to have it in the station in case of any emergency and we lose power, we can throw any battery that we have at this from any tool or anything like that, and we can continue operating our station. I'm going to cover ordering the components with the price and all that, the unboxing all the parts, putting together all these pieces, this box that I see here above me. And then we're going to do a set of analysis of the inputs and outputs. We're going to measure some of combinations. In this video, it's going to be too long to test ripple, spikes, and all these kind of things, or testing RFI or EMI. We're going to do that for a part 2 of this video, and this is what is coming next after this part 1. This is how I got inspired to build this project. I was watching a video from Kevin, Kilo Bravo 9 Romeo Lima Whiskey, to produce a stable and clean 19 volts output for his laptop. He lives most of the time on an RV, converting the power from the RV to 110 volts and then hooking up the laptop using the laptop power supply into an inverter. Is something that it does a double conversion and is very inefficient to preserve the battery and the power that he has on his RV as he lives off-grid, right? So he put together this converter that delivers 19 volts. It is what he needs for his laptop to work. And you can see here on his multimeter is showing 18.77 volts. Is always close to nominal voltage that is advertised. There is here the miniature if you want to go and watch his video. This is a different project, it's different voltage and different purpose, but the inspiration, I got it from him. One of the things that I forgot to mention earlier is some radios, they expect 13.8 volts. They don't work very well with 12 volts. Here, I am leaving for you an example. This is a video from Steve, November 4, Lima, Quebec, that you can search. Here is the title on the screen. And he does all the tests with 13.8 volts, and then he lowers the voltage to 12 volts, and he shows how this ICOM 7300 start performing really, really bad, and and transmitting sidebands in CW that it shouldn't. And that is another reason why, even if we operate with 12-volt batteries, we will like to get always 13.8 volts out. Here I'm going to leave you a very simple to understand diagram of all the components and how this stabilizer works. So as input we can use any kind of lithium batteries, any kind of tool batteries, as you can see here. Lead acid batteries, and also you can use lithium batteries, 12 volts, you know, the big packs, and you can use any system that is charged by solar panels, and in those systems it goes over 12 volts. Some of those systems are 24 volts and some of these systems are 36 volts, so that will be no problem to connect to your radios using this stabilizer. So from any of these sources, the connector goes to an input mirror that is going to help us to identify the input voltage and how much this chain is consuming. Then after the input mirror, it goes to this RFI EMI filtering that is on the input of the converter. The DC to DC back boost converter takes care of providing 13.8 volt stable in the output. The output goes to this second RFI EMI filter to ensure that it's clean. From that, it goes to the output mirror where we can monitor that we are truly delivering only 13.8 volts and no more or less than that. From there, we connect to our radio equipment. And these are additional optional components that I use. These are the XT60 connectors for the input. I use these connectors typically on use on the radio control toys for any sources that are above 13.8 volts, like 20 volts battery or 40 volts battery. Anything that is above 13.8, and the reason I use a different connector is to don't make the mistake of connecting a higher voltage battery to the radio directly by confusion, right? So for any battery or use power pole connectors, this is for all 13.8 volt sources and radios. And silicon wires. Silicon wires prevents when the higher consumption, high amperage is happening. Those cables sometimes can get warm and you don't want them to melt. Switches are independent switches for input and output power, so we can turn on one stage at the time to ensure everything is working fine before delivering the final power to our expensive radio equipment. And this is the last piece of info that I have for you before we jump into the unboxing of the parts. So here is the screenshot from the order from AliExpress, so you can see how much I pay for each one of the parts. For the DC to DC up-down back converter, 13.8 volts, I pay 62 Canadian. For both power filtering units, I pay 14 Canadian, and for both input and output mirrors, I pay 21 Canadians. The total is 98 Canadian dollars, and that converter to USD dollars, American dollars, is around $70. I leave also the main product ID here for all the most important parts that I use for this build, in case that you want to order the exactly same ones, if in case that you want to build this yourself. Alright, what I have in here in this box is all the components that we need to build our perfect 13.8 volts power regulator. So I'm gonna take the items from here. I'm gonna show one by one to you to see all the parts and different things that we're going to use in this video. So now in this section of the video, I will go through all the parts that we have in here. I'm going to introduce all the parts that we're going to use in this project to you. So some of these parts I already have and some I purchased specifically for this project. So for example, this cable we're going to use It has power poles in here, connectors, and we're going to use to connect to, for example, the drill batteries. The drill batteries can be 12 volts, or it could be 20 volts or 18 volts. So we're going to use this to connect to these batteries. In here, we have dummy load for the power supply, right? So this is dummy load, has two resistors, 3 ohms each, 100 watts, that are mounted over a heat dissipation metal bracket. We're gonna need that for our tests. Now, for to switch the input and output, we're gonna use a couple of these double throw switches. So we cut at the same time the negative and the positive of the battery input or the power supply output in this case. So we're going to use a couple of these. Also, I have from before, I have this box with power pole connectors that we're going to use for some sources that are 12 volts. We're going to use these power pole connectors so we don't mix the sources and we avoid confusion and maybe burning something. For the 20 volts, 18 volts, 40 volts batteries that I have, I'm going to use these connectors. Those are the XT60 connectors. So we're going to use these. Should make sure that we don't mix up the voltages. And to build some adapters, in case that we want to connect stuff directly with wires, I purchased these adapters that it has levers. You can see here, you open the levers, you put the cables inside there, and you can connect anything you want. So I'm going to build, with these adapters, I'm going to build a couple of connectors, one with XT60, another with the power poles, so we can use something that is wired directly instead of the normal connector. So the next is the cable that I'm going to use through this build. Is a cable that is silicone cable, 12 gauge. So you can see here is a 12 gauge, 200 degrees Celsius. This cable is good, so it's not going to melt or burn. For the filtering the input and filtering the output, I got a couple of these RFI EMI reduction units or filtering units. As you can see here, the unit has your input voltage in here, and whatever you connect the load in this side, it has 3 connections, positive, negative, and the middle one is for ground in case that you want to use grounding. So I have a couple of them, one for the input, one for the output. And if you ask me why you're going to use the input if you're planning to use batteries, yes, I'm planning to use batteries mainly, but also I wanted this to be for any energy device that I have. So it could be Chinese power supply that maybe is not that clean in the output, and with this double filtering, we will be able to clean that before we inject it into this new device. And the other one is for the output, which is for the start of this build, which is this module here. This module is also switching, so we need to clean the output. And as you can see here, is a DC to DC converter. It has an input that can be anything from 8 volts to 40 volts. And the output is a constant 13.8 volts, or around 13.8 volts. We're going to measure that 30 amps. Okay. So the last part that we're going to use, that also we have 2 of them, is these 2 power meters that we have in here. Those are very common devices. Those are not new. Those are has been around for a while. This is a high precision water meter and power analyzer. And we connect the energy source on this side, and in this side the load, and we have 2 of them because we're going to measure the voltage and the consumption in the input, and also measure the consumption and amperage at the output with this other second unit, which is exactly the same. Those are very cheap, so better to put 2 of them instead of 1, and we can measure all the times separately. This is all the parts that we need. So now next we're going to start putting the things together. So now the idea for this build is here in this prototype that I put it loose here on my bench. We have the input Here is going to be this XT60 connector. We're going to use for any 13.8 volts. We're going to use this connector in the input. So we're going to put these two in the input for the different sources to power our circuit. Here we have the switch that is going to cut the input. We have the power meter, the first filter, the converter unit, the converter from 8 to 40 volts to 13.8 volts, another RFI filtering unit, the power meter at the end that is going to measure the power, the voltage, everything at the output. We're going to put a switch in the output that is going to cut our radios, anything that is connected after, and the output, it will be with power poles for connecting all our radios. So now our input sources could be, like I mentioned, like maybe a bad power supply, like a PC or a server power supply. It could be this battery. This is a 40 volts battery from a Hoverboard. It could be this battery. This is a 12 volts battery from a power tool. Or it could be this. This is an 18 volt battery from a Makita power tool. Or you can use this 20 volts battery from a DeWALT power tool. So with any of these batteries, with this device, we are going to get a clean 13.8 volts at the end. That is the prototype. This is what we are trying to build here. Now in this section of the video, I'm going to show you the mechanical assembly of the components in the box. So this is the outside, the module, so it can vent. It will be sitting outside, and of course the power meters for the input and the power meter for the output, so we can see if we can read them, will be of course outside the box. So let me show you what is inside the box. Inside the box we have is loose, is not fixed to the box yet because I'm checking the position of the elements. We have the two RFI suppressors inside. They will be mounted into what is a PVC piece, right? So this is to isolate the connection from the bottom of these modules from the metallical box. The other reason of using a metallical box is to contain all the RFI from these things inside the box. And now let me show you, this is one of those, if you remember, all of you, one of those switches for the keyboard and the monitor to handle two different computers, right? So I adapted this box. I put on this side the power switches for the input and the output, and the XT60 for the input. The 8 to 40 volts input will be here, and the output in the form of a power pole connector will be on this side for the 13.8 output of this box. All right, now with the interior connections all finished, let's do a quick walkthrough, and before we close the box, and then we're gonna start doing all the testing with the box closed. So as you can see here, all the white shrink is all the connections between the different parts. All the cables that were very short that come with the parts, so I have to extend them with the silicone cable that I shown earlier. So how I done all these connections, I use these crimping connectors, but I remove the blue protection, and then I crimp and I solder after crimping for a more secure connection between the different parts. I don't trust crimping alone. Sometimes crimps can come loose, but if you crimp and solder, then it's a connection that is gonna last for life. Everything has been done like this. Everything that has that needed that extension, like all those. Then in this side we have the XT60 for the input. And on this side we have the power poles for the output, and you can see the two RFI suppression units here with the grounding in this point. So the grounding, I come into the middle connector in both of them, and it's a line that runs through the end, so it doesn't need to be connected here because it's the same line that goes side to side. So that is the conclusion of interior. Now I'm gonna close this and we're gonna power on and start doing some tests just to see how this performs and if it's fulfill its purpose. All right, so now the build is finished. So we are gonna take a quick look for the exterior of the unit just to see how ended up with this power stabilizer. So we have the two power meters, one in the top for the input, one in the bottom for the output, and in the middle we have the module. On the left hand side we have the ground connection is a bolt in here with a nut. On the right side of the box we have now here, let's see if the camera is focusing. On the right side of the box we have the input 8 to 40 volt DC with the independent power switch, and then on the other side we have the output 13.8 volts and power pole connector and the independent power switch for the output. So now let me connect a variable power supply just to see how everything behaves, and we're gonna start testing with then after that with different power supplies and different type of batteries and of course loads, and at the end we're gonna do an RFI test just to make sure this is not introducing any RFI, and a load test and final test with the radios. So now we are ready to do the power on and variable input testing. For that I prepared several things here on the bench, as you can see. First of all, here this is a little variable power supply that goes from 0 to close to 40 volts. The unit I have below this, it can go only to 29 volts, so this will reach probably around 28 volts maximum, so we can test with this voltage maximum for now. Here we have a multimeter that we're going to use to, in conjunction with the output here, to measure the output, just make sure this is accurate. On this side we have the resistors for is a dummy load for DC voltage. This can go up to over 2 amperes, so we will have to see when we can use. With very low voltage like 8 volts is not going to work. It's going to try to consume too much and it's going to shut down. So once we start increasing the voltage, we're going to connect this charge and see how the system performs. So now let's turn on the 8 volts, which is the minimum that this unit works, from 8 to 40. And let's turn on the input. As soon as we turn on the input, we see here on the display also 8 volts in the input power meter. In the output power meter, we already see 13.75 volts output, but there is nothing coming out to the multimeter because I haven't turned the output on. So now I'm gonna do that, and now the meter is showing 13.76 volts, which is 0.1 volt different from this meter. So these meters are pretty accurate. In the input, I don't use a separate meter because I have the meter here right into the power supply. And you can see the system in standby mode, not doing anything, is consuming around 180 milliamps. Okay, so in standby, it's consuming 180 milliamps. Because it's running some stuff in here on the module, and is running these two things, right? So in everything together is around 170, it goes up and down milliamps. Okay, so now when I increase the input voltage, I'm going to keep an eye on the output. Just make sure there is always below 13.8 volts. So you can see I'm going up, and you can see also is going up there. So I'm going to stop around here like 14.55 volts. You see I have very similar reading on the power meter for the input, and in the output I am still in 13.74, which is pretty good for our radios. So I'm going to keep going up. Of course, the current draw, it depends on your input voltage, right? So for example, now if I'm feeding this thing with 20 volts, it's only drawing 51 milliamps to 80, you know, it goes up and down. And you can see here also how much is drawing from the power supply. And of course here nothing, because we haven't put any load. But now with 20 volts, let's see if this little power supply can support this load. I'm not sure of that. Let's give it a try. Let's see if we can get it working. So in this part here, I have like a bus that I connected the meter and different things. So let me connect the positive of the battery, and now with feeding this with 20 volts, we are outputting 2.27 amps into the resistors. 2.27 amps into the resistors. I'm touching the resistors here to see if they are getting hot. They are not getting hot yet. The module is not getting hot. So this is all pretty good. Because there is load in here, this meter is showing now 13.53 volts, but here, this is right out of the output of the module. We still see that the module is delivering 13.73 volts. So I'm going to keep increasing the output here. I'm keeping my hand here on the resistor just to make sure it doesn't get too hot, and I'm going to go to the max in here. Here up to the max, it will go around this voltage, 20 something, maybe 28, I'm not sure. Yeah, 2875. At 2875 volts is delivering less than 1.5 amp, this variable power supply. Here is showing me that I'm consuming 1.25 amps. So there is a little bit of discrepancy in there. And here in the output, I still showing 2.28 amps. This is going to be always constant, and is always constant the voltage. Even I am feeding almost 29 volts, I am always having 13.3.75. So at the end, so this is really hot now. This is not even warm. So I want to connect the resistors just to prevent them from burning, so I don't forget. And in here, let me see if I can get the reading. Yeah, this is not even warm, the module. All right. So for this part of the tests, we're going to stop here, and we're going to do a different test after the cut. Now we're going to do a high current test. So how we're going to do that? As an input, we're going to use this AGM battery. It's a 12 volt, 35 ampere hour battery that I take with me when I do mobile portable operations, POTA, all these kind of things I take with me. And one of the things that happen with this battery is it starts over 12 volt, close to 13 volts, and then it goes going down up to 11 or a little bit less than 11 volts, which is not very good for the radio. And this is the main reason I built this thing. So we're going to test now connecting this battery that has power pole connector. So we're going to use our adapter. We use the adapter from power pole to XT60 to connect in the input. And now we have the battery connected in here. We're going to see how much voltage it has. 12.67 is the voltage that the battery has. The output is what you want in your radio, 13.75 volts. I'm going to turn on the output, and we have same thing here on the meter. And what I have here on the left is DIY load, 12 volt halogen lamps added in parallel over this rail that we have in here. So I have 8 halogen lamps. They're not exactly all the same. So I wrote here by one how much each one consumes at 13.8 volts. So each one consumes between 3 amperes to a maximum of 4.45 amperes, the leftmost one here on this arrangement, okay? So from the output here, it goes into the other end of the arrangement. And here I have connected the multimeter just to see at the end how much voltage we have left. So let's start this. Let's turn the first one on. So that it caused a glitch in here, as you can see. I don't know why. So to turn it on, the light cause a glitch here. It's showing that it's consuming 4.5 amps. In the input, we are consuming 4.87 amps, and the voltage is 12 volts of this AGM battery. So I'm gonna add one more of these lights. With one more light, this goes still 13.73, close to 7.58 amps. In the input, we have 8 amps, and the battery is dropping to 11.52 volts. But even the battery is dropping 11 to 52 volts on the input, the radio always it gets 13.75 volts, and this is the big difference of using something like this. So I'm gonna add one more, and with this we are close to what probably will be 100 watts. Yes, on the radio is 13.73 amps in the input, consuming the battery drop to 10.66 volts. And here for some reason this power module goes bonkers when I add the power. I have to see if with the radio happens the same thing. This is something that I'm just testing this the first time, like you seeing this in real time. I didn't have a chance to test this before. So, but still, we have at the end 12.57 volts after all the consumption left. So let me turn all these things off, because it's starting getting really hot. The module is not even warm. The module is not even warm, and the battery is recovering slowly. It went back to 12.50 volts. In this part, I have hooked up the Hoverboard battery. This is a 40 volts battery from a Hoverboard. You can see here in the input power meter is showing 40.34 volts with almost no consumption. In the output, as always, 13.79, 13.78 on the meter, so pretty accurate, pretty close. This is what we want to be. So this is a little bit over 40 volts, so it's like pushing the module. The module is a little bit warm after I connected this 40 volts with no load. So let's add some load. Here I have the resistor pack, so this will add a couple of amps into this. So let's see, 2.24 amps in the output and 0.81 amps in the input. The voltage dropped a little bit on the meter because it detects the load. 13.6 on the meter, and still here on the power meter is 13.77, which is right after the converter. So there is some cables resistance in between. We are measuring through all these cables and alligator clips and all that. So this is holding up. It's a very low current, right? 2.26 amps. Later we're gonna test with the radio, just to make sure is holding up to spec. So what we want to see if it works with the radio or not. But now we are doing all these preliminary tests because we don't want to hook up a radio and burn it, right? So we want to make sure this device works well before we even attempt to hook up any of our expensive radios. So this is not too warm. I can touch it. It's warming up, and I think it's because it's getting the upper limit of the voltage, right? So it has to reduce from 40 volt to 13.8. and is doing well so far. So we're gonna switch the battery with something else, and we're gonna continue testing. Let's keep testing with different batteries. Right now here I have a 12-volt Milwaukee tool power tool battery connected to the device. Let me turn it on. Okay, this is reading 11.70 volts from this 12-volt batteries, so it's not fully charged. Output again 13.75, 13.77 is always a little bit below 13.8. Let's turn the output and check here on the multimeter, 13.76 out of this battery, and let's put the resistor pack to draw some amps. So we are drawing 2.27 from the 13.8 volts output, and we are drawing 2.86 amps from the battery. Of course, we are drawing more from the battery because it's a lower voltage. Let's move to a different battery. All right, let's try this Makita 18 volts. Let's turn this thing on. All right, this is fully charged. This Makita is providing 20.72 volts, 13.73 in the output. Let's turn it on. All right, 13.74. And again, let's put some load and let's see if the Makita can take the load. We have always 2.27 up with this resistor pack. And the Makita is providing 1.60 amps at 20 volts, as you can see here on the meter. All right, let's move to the next battery. And now this is the last battery that I have. This is also a 20 volts battery from DeWALT power tool. This one is 1.5 ampere hours. So let's turn on the device. So this is also fully charged, 20.58 volts. You can see here on the input. On the output, always below 13.73 volts. Let's turn the output out. We double check the output on the multimeter. Is within the specs, and we put the resistor pack here to draw some current from the battery. Again, always is this voltage is always drawing the same 2.27 amps, and from the 20 volts battery is drawing 1.62 amps. Very similar numbers that we got from the previous battery, the Makita one, that has the same voltage. So again, another battery that we can use with our radios. Of course, this probably is not going to be good for 100 watts, but for QRP radios or listening, just is going to run perfectly, or maybe just running the radio in low power will run with no problems. So what we have here now on the bench for the next test is a very high power supply. This is a Gigabyte 750 watts. This power supply delivers on the 12-volt rail 61 amps. This is what is rated, what it says on the label. This module on the top is a module that connects to the output of that goes into the motherboard. This an AliExpress module, and allows you to turn on the power supply and to get the power from all the rails on these screws that you can see here. So I connected to our voltage stabilizer here, the output, and I'm gonna turn it on. And when I turn it on, we see that the Gigabyte power supply is delivering 12.07 volts, and in our output, of course, always 13.75 volts. I'm going to turn on, no, the output is already on, so we can see here also 13.76 volts in the output. And we are going to test once again with the resistor pack. We're going to add this load, and with these loads, we are getting 2.27 amps on the output, on the 13.75 volts output, and is sucking from the power supply 2.70 amps from the 12-volt rail. Using this type of module, as you can see here, you don't have to modify your server or PC power supply to get the 13.8 volts that you need. Just you directly connect and it will work with any PC or any server power supply that has enough amps, enough power to run your radios. Of course, later we're going to test if we don't have RFI on the output. This is why we installed these two modules inside, to use this type of switching power supplies that usually when you connect directly to the radio, without this, it has a lot of RFI. So now we are going to start with the real tests. And what I have here on the bench, I have my FT-857D Yaesu radio to do all the testing. The RF power set is set to 75 watts or 75% maximum power output. It's connected to into a dummy load. And here in the back, we have our power stabilizer. Is getting the power out of this 12-volt AGM battery. Is getting 12.37 volts from the battery and 0.86 amps, and is putting out 13.75 volts as usual, and at 0.74 amps. This is what this radio consumes on standby mode, which is pretty high. So what we are going to do is I'm going to show you some of my findings already on this radio. So the radio is set up in FM mode. And the external meter, I have here the power output. So I'm gonna key the radio and we're gonna see what is happening when I key the radio at 75 watts of FM. The radio is transmitting. The consumption here goes to 20 amps. It keeps increasing because the battery is dropping. So 22 amps. So we see that the radios keep transmitting, 22 amps, 23 amps, the battery is dropping, 24 amps, the radio is still transmitting, and then the radio dies. The transmission dies. What happened is it stops at 25 amps. And I wanted to see at what point the module shut down itself. And I got that point is set to 25 amps in the input. Again, this is consuming 25 amps because the battery is 12 volts battery. So we're going to try with a higher voltage battery and we'll see if this happens in the same way. Okay, so I'm not going to do it again because I don't want to damage the radio during the tests. But we see that on the previous test that at around 25 amps, the module shuts down. All right, so let's do this test now once again. The radio is still set at 75 watts. I connected the lithium-ion battery from Hoverboard. This battery is providing, as you can see here on the module, 40 volts, which is the maximum that this module takes. It's consuming 0.34 amps at this voltage, and the output to the radio in standby mode is 0.72 amps and is providing 13.77 volts. So now we're gonna try doing a transmission at 75 watts and see if the battery can take it and the module can take it. So let's take a look. Let's see what happened. Yeah, no problems. So everything seems to be fine. Radio is transmitting at 75 amps. The module is putting out 12.53 amps and is taking from the AGM battery, from the lithium battery, 4.61 amps, which I was telling you earlier that will be the case. At higher voltage, it will take less amps, and the module doesn't seem to be shutting down. So at 75 watts works. So we're gonna try at 100 watts. So first we're gonna do a touch. Yes, the dummy load is getting really warm. So we're gonna keep the next one short. The module is not warm at all. It's a little bit warm. So here we are gonna increase, as you can see, from 70 watts to 100 watts, which is the maximum in FM mode. It's gonna put 100 watts out. So let's key the radio in for a brief moment just to see if everything works fine. All right, we are transmitting 100 watts. The output at 100 watts is 15 amps, 15.60 amps. The input is 5.81 amps. With the battery here from Hoverboard, it seems to be taking this very, very good. So we'll see, we're gonna keep it just a little bit more. And what I suspected, probably my 12 volts battery was not good enough for this test, right? So the dummy load is very, very warm, so I'm not gonna keep trying anymore. But the module is working as expected. We know that probably we will need more than 12 volts for keeping the output stable and to preventing the module to shut down itself. But at 100 watts, it works perfectly with more than 12 volts. So I'm gonna try one of the other smaller batteries and we'll see how that works. All right, so this is the last test that we are going to do. So the radio is set up at 75 watts. You can see here at the bottom top right corner the Makita 20 volts battery. Everything is connected now to this battery. With the module is getting 20.39 volts. Is consuming from the battery half an amp or 0.55 amps, and is delivering 0.74 amps as usual at 13.73 volts as usual. This is what this radio in receiving mode, in standby mode, is consuming. So now what we are going to do is, let me check the dummy load. The dummy load is a little bit warm, so I'm going to do shorter transmissions, not as long as before. So radio 75 watts, let's key in. So now with the key in, 75 watts out, the battery is delivering 9.40 amps and the module is delivering 12.55 amps at the 13.8 volts that we expect. So we're gonna stop here. I'm checking the dummy load. Is very, very warm. I don't want to just burn the dummy load. We're gonna do the last test. We're gonna go at 100 watts maximum power for the radio. And remember, we are just powering the radio and transmitting out of a battery from a power tool, okay? And converting the 20 volts from the power tool into the 13.8 volts that this radio need with this module that we built. So now we're gonna key in with 100 watts. Let's see what happened. The radio is transmitting okay. So far, no problems. In the module, in the input, we have 12.14 amps and the battery is supporting that very well. And in the output, we have 15 amps at 40.43. And again, everything is working fine and the radio is still transmitting. So I'm gonna stop so I don't burn my dummy load, which is very, 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 very hard to the touch and cannot keep it. So I will call this a success. If we carry these couple of these batteries plus another 12 volt batteries, we can probably keep running the station for the entire day in portable mode. So here you have it again, folks. This is the device with the Milwaukee battery still running. The Milwaukee has a 11.15 volts power. Device is still delivering 13.75 volts. This is the same thing I show you at the beginning of the video, and you can see this is working as expected. So I hope you liked the video. I hope you liked the project. Please stay tuned for the second part for this project, where we're gonna dig deeper into the RFI interference and see how that clean or bad is according to the input. Thanks for watching, and until the next time.